Today, in just 3 minutes, we'll fully break down the CAN bus. CAN serves as a shared communication backbone that allows all electronic control units in vehicles and industrial machinery to transmit and exchange data with each other. In terms of hardware, there are just two wires, CAN H and CAN L. They send signals by using the voltage difference between the two lines. This is what we call differential signaling. There are basically just two signal states in CAN, dominant and recessive, and the dominant one always gets higher priority. 120 ohms terminating resistors must be fitted at both ends of the bus. They match the line impedance, eliminate signal reflection and data errors, and ensure stable communication. Relying further on wired and logic, multiple devices can share the same bus without mutual interference. Understand the basics, and then let's see how CAN works. Every single set of data sent between CAN devices is what we call a CAN frame. There are two main types of these frames, standard and extended. The ID determines message priority. The smaller the ID number, the higher the priority. A CAN frame starts with the start of frame soft bit. The ID determines message priority, while the order and IDE bits distinguish frame types. The DLC defines the data length, and the data field carries the actual information. CAN's core advantage lies in non-destructive bitwise arbitration. When multiple devices transmit data simultaneously, lower priority nodes back off automatically, resulting in no data conflicts or message collisions throughout the process. To wrap things up, let's bring it into real-world practice and talk about how this actually works in application. In practical engineering, 80% of CAN communication failures originate from the physical layer. Wiring errors, termination resistor issues, and electrical interference are the most common problems. When troubleshooting, always prioritize hardware checks. Two core tools are essential for daily debugging. First up is a CAN analyzer, and the second is a PC-based debugging software. The DBC file acts as the core data translation file. It converts raw binary CAN data into meaningful physical quantities, such as rotational speed and voltage. Currently, the CAN bus has been widely used in multiple industrial fields. It can be found in passenger cars, new energy, construction machinery, and the shipbuilding industry. As equipment requirements continue to upgrade, CAN technology keeps evolving iteratively. Following standard CAN comes CAN FD, featuring faster speed and larger data capacity. Next in line is the next generation CAN XL with ultra-large data throughput. It fully meets the communication demands of complex industrial equipment in all aspects. Beyond standard CAN bus compatibility, our products also fully support CAN FD, delivering higher bandwidth and faster data transmission to meet the evolving demands of modern vehicle and industrial control systems.